So good evening. Thanks, Professor Holz, for introducing me and also giving me an opportunity to talk to you about one of the latest catastrophe worldwide. This is one of the most catastrophe, worst one. And I'll be talking about, I'll be restricting my talk to the Indian coast. And if you see, I come from this location, so which means that I have a very important role to play as far as this protection of the coast is concerned. So I have organized this course considering that the group which I am going to face is a heterogeneous group. So I am sure that some people will be interested in fundamentals and some people will be interested in complicated mathematical functions. But I cannot satisfy all, so I would rather restrict my talk to the most starting from the fundamentals, so that what went wrong and what is happening, and slowly I will take you on to the planned mitigation measures particularly for the Tamil Nadu coast. So the organization of my lecture would be the difference between waves, tides, currents and tsunami. But the most important is what exactly is a tsunami, the definition, its travel, and some of the past events. Then I will try to talk something on the cyclone, wave, as well as the tsunami, the difference. And probably I will not touch on the warning system, because there seems to be still a big question mark concerning the warning system. And then some of the satellite imageries as well as the safety rules I will try to touch upon. The main difference between ocean wave and a tsunami is the ocean wave is an oscillatory motion. That is, we all have undergone such kind of a motion. Oscillatory motion is you have motion like this. So you have a simple, it's nothing but a simple harmonic motion similar to the pendulum of a clock. So when structures are exposed to the action of ocean waves, the type of failure it undergoes is a fatigue type of failure. Whereas in the case of a tsunami, it is still called a wave, but it is a very, very long wave. The tsunami will not be moving as a wave, because it will be moving as a wall of water. So its dynamic thrust in the direction of propagation will be quite enormous compared to the wave. And the speed with which the tsunami will be running closer to, right from its generation point, is just that it is going to be directly a proportional, a function of the water depth. So this is the main difference between ocean wave and a tsunami. So to have a further sort of a mathematical or this physics, from the physics point of view, I just use this illustration to explain how a wave is different from that of a tsunami. For example, a wave which is moving right from the deep ocean has the uppermost point, which is called as a crest of the wave. The bottommost point is called as the trough of the wave. The distance between any two successive crests is called as the wavelength, and the time taken for the wave to travel one wavelength is called as a wave period. In the case of an ocean wave, the normal ocean wave, the wavelength is of the order of meters, whereas in the case of tsunami, it's the order of kilometers. And the time taken, that is a wave period, that is to travel one wavelength, the time taken in the case of a wave is few seconds, whereas in the case of a tsunami, it's from few minutes to hours. So that's the basic difference between ocean wave and a tsunami. And in the case of an ocean wave, why we don't really feel its impact on the coast is, the reason is that most of the energy, when it reaches the coast somewhere before you stand just near the shoreline, the entire energy contained in the ocean waves break and the energy is lost, and then you have a gentle uprush of the water. So why the waves break here? Because there is no rise in the water level, and you have only little water depth when the wave is going to break. But in the case of a tsunami, there is a rise in the water level, and you have enormous amount of water running into the ocean, running along the coast, running to the coast. And that's the reason the waves will not be breaking near the coast. So this explains clearly the difference between an ocean wave and a tsunami. What is a tsunami? Again, a tsunami is nothing but a wall of water, which I have already told you. And a tsunami is a series of waves, that is giant waves, with wavelengths of a few kilometers and period from ranging between 10 minutes to 2 hours. In the case of wave, it's few seconds. And this results from displacements. Actually, this type of a tsunami results from displacements caused by large earthquakes. Not all earthquakes would cause a tsunami, because there are several earthquakes in the ocean beneath the seafloor. But all these earthquakes do not really cause the tsunami. It is only the vertical displacement of the plates, what do you call this, the rock beneath the seabed, which tries to create this kind of tsunami. Tsunamis are often incorrectly called as tidal waves. Even in the case of the Indian Ocean tsunami, initially the media was calling it as a tidal wave. It took several hours for them to correct themselves and call it as, to realize that it is a tsunami and not a tidal wave. The speed of the tsunami is around 500 miles per hour and reaches heights 50 to 100 feet. In an open ocean, its height is just 1 meter. So people who are in the ocean, deep ocean, when you have a tsunami being generated, they will hardly see the tsunami. The energy released in the present tsunami is something like 4.75 lakh, that is 10 to the power 5 kilotons. That is something like 23,000 times the energy released by the atomic bomb that destroyed Hiroshima. So in deep water, that is greater than 25 meters in the ocean, tsunamis are rarely over 1 meter. And it will not be noticed by ships, and that is what I told you earlier. And these tsunamis try to move in radial directions from its source. For example, if you drop a stone in the ocean, open ocean, or open pond, you see how the disturbance moves. If there is no obstruction, it moves only in radial direction. The same thing holds good in the case of a tsunami. How fast the tsunami can travel? The tsunami is dependent just on the water depth. So its speed is just, velocity is just square root of depth into acceleration constant. So tsunamis travel approximately, in the present case, that in the ocean, Indian Ocean tsunami, at the generation point, at the source point, the tsunami was expected to travel with a speed of 713 kilometers per hour. So you can imagine that of a jumbo jet. And this is in a water depth of 4 kilometers. This is where the tsunami generated, somewhere near Sumatra. We'll come back to that later. In 10 meters of water depth, this velocity drops down to 36 kilometers per hour. We'll have a further look at the illustration of how this behaves. Now, moving on to tsunami statistics, you see that there has been enough number of tsunamis, most of them in the Pacific. And not all the tsunamis are damaging ones. When I say damaging ones, it involves the loss of lives. And only a few of the tsunamis have been really damaging ones when you compare the total number of tsunamis. Why does this happen? So this is what is called as the movement of plates. Millions and millions years back, all the continents were, it is believed that all the continents were together. For example, if you look at India now, you can see that India just goes into this space, and then if you put everything together, it will form as one piece. So millions and millions of years back, they got split, and this is what is called as the continental drift. So when beneath the ocean floor, you have what is called as faults, that is rocks. So they will be one above, they will be clinging on one to the other, and if subduction takes place of one of the plate over the other, that is, if there is a vertical movement of one of the plate against the other, then you have a lot of energy released in the water media, and then you have the tsunami generated at the surface, and then it will start moving in radial direction. So this again I would like to project how it really happens. So you see the two faults, one going below the other, and then you have the generation of the long period waves, and then it moves radially, and it will attack the entire coast right from the source point. So this is in plan what we have seen. Now, in order to understand a bit more clear, if you look at this, these are some of the faults. So you see there are two faults, one gliding over other or getting released, which is called a subduction. Then you have the increase in the wave heights close to the shore. For people who are working in the coastal engineering, you know that the power contained in a wave is a product of energy, that is a function of wave height and the wave period. In the deep ocean, the wave period is large, and when it is wavelength is large. When it comes to coastal waters, the wavelength gets reduced. But as per the conservation law of the power should be same. So this leads to the amplification of the amplitude or the height of the wave, and that is the reason why you have the building up of waves. Apart from, there are other phenomena which I am not going to touch upon. Now, tsunamis, in fact, tsunami was quite new to India. I am not going to talk about the worldwide scenario. We have enough information. But when we looked at some of the net, some of the web pages, then we see that tsunamis are not so new as we thought. For example, August 83, there was an explosion of Krakatoa volcano in Indonesia. The animation of this, which we will be seeing later, wherein the east coast of India was affected, and we had a 2-meter tsunami recorded in Chennai. That is the city where I come from. And 26th June 1941, on a Richter scale of 8.1, earthquake in Andaman. That has resulted in tsunami, but along the east coast, but we don't have the real estimate of the height of the tsunami. In 1945, we had an earthquake somewhere 100 kilometers south of Karachi that has resulted in a 12-meter tsunami in the Kandla port, that is near Gujarat. And Andaman and Nicobar Island, I think some of you are okay with the geography. Anyway, we'll quickly go into the map also. In Andaman and Nicobar Islands, since 1973, a dozen of earthquakes in its vicinity of around 5 to 6 have generated, but we have never had any tsunami. So all earthquakes do not really generate tsunamis. So this is the one which was a Chile. This is a worldwide scenario. In Chile, there was one tsunami which was generated, and the tsunami traveled something like 17,000 kilometers all the way to Japan, killing about 200 people. So this is a numerical animation by one of the universities in Korea. And then we see now, so this is somewhere near the Krakatoa Island in the Indonesian country, and then you see this tsunami has traveled all the way to India, and this is Chennai somewhere here. So it has reached Chennai. So there are enough evidences and also the numerical simulations which show that such a situation has occurred. So when we talk about tsunami, now for the mathematicians or for the physics, what exactly is the problem? Okay, we have enough number of numerical models which can simulate the behavior of waves right from deep waters to the shallow waters. Once you know the bathymetry, that is the bathymetry in the sense the depth of the ocean right from the deep waters, you can very easily simulate how the wave is going to behave when it reaches the ocean, when it reaches the coast. And Professor Howells has also enough number of numerical models to look at it. But still there are a number of problems in connection with the correct way of simulating. One point which is yet to be resolved is how much of the energy is being released at this point. So that is something which is a big question mark, because this is something to do with the amount of energy that is being released when one fault goes below the other, because the entire disturbance at the source is dependent on this the amount of thrust that is being released. So which is going to control the generation, that is where we still have a question mark. Propagation, numerically we can model the propagation, that's not a problem. But then the inundation, this is where you still have a lot of problems. For example, you have to include the reflection from the coast, then numerically you have to, exactly, you have to simulate the seabed profile, etc. So there looks to be a lot of work yet to be done in the case of evolution and generation of tsunami. Now, going back, why did this 2004 tsunami occur? We all know that this is because of the plates which are moving beneath the sea floor. So earthquakes occur when any of the plates collide on their boundaries. What exactly is plate? We will see it very quickly. So scientists believe that one plate that comprised the landmass from India to Australia has broken into two. So initial eruption was 8.9. So 8.9, even 0.1 matters as far as the Richter scale is concerned in terms of energy that is being released due to an earthquake. So the initial 8.1, later which was estimated to be 9.3, eruption happened near the location of the meeting point of the Australian, Indian and the Burmese plate. Scientists have shown that this is a region of compression as the Australian plate is rotating counterclockwise into the Indian plate. So let us not go into the details about the plate tectonics and the geological aspect of it, but what we need to know is the next thing is the tsunami originated in that subduction zone. That is, when you have two plates, one plate is going below the other plate. So it is something like one plate going below the other plate. Over what length? Over 1,200 kilometers and over a width of 100 kilometers, over depth of about 20 meters. So you can imagine the amount of energy that can be released. You are talking in terms of 1,200 kilometers, the plate is going to move. So that is, this figure explains the lines of ruptures, and this is the point. So this is, you have the Australian plate, and this is the Indian plate, and the Burmese plate is here. So somewhere here you had the problem of the plate, one plate going below the other, and that's the problem. So now, so you have the different plates, etc., shown here, South American, etc. So we will not move into the details of the plate tectonics. But how does these plates move? So these plates can move in different ways, as can be seen in this small animation. Now, what happened in the case of 2004 tsunami? So in the case of 2004 tsunami, we had the Indian plate, which we have seen in the earlier slide, and we have the Burma microplate. So somewhere here, this is the area where you had all these shocks, etc. So what has happened is, this has not only moved in this direction, but also there was a move in this direction. So that has created the eruption of the tsunami. Location, most of you know that the location is given here. It's all self-explanatory, and the countries affected are India, Sri Lanka, Malaysia, Indonesia, Thailand, Bangkok, Bangladesh, as well as Somalia. But if you look at some of the animations, the moment we had this tsunami, the first animation was showing how it was available, but prior to going into the animation, we'll just look at the seismographic records. This is the source is Columbian University, New York. So the seismographic record obtained on the 25th of December is shown here. It looks very smooth. There is not much of problem. And you see during on 26th September at 26th December at 12 hours, the kind of disturbance that itself clearly demonstrates that there is something very strange that has happened here. So when you have a tsunami, is there an initial warning? Yes, of course there is an initial warning. That is, the initial warning is the recedence of the water line. When you stand on the shoreline, you see that the water line in front of you will just go into the sea for a long distance. And that itself is an initial warning. Unfortunately, since all these informations are known to the people living along the Pacific, but not along the Indian Ocean, because we have never had any such experience. So when the water line receded into the ocean, so people thought that there is something funny happening, but so unfortunately these people, they went out of curiosity, went into the ocean. Unfortunately, you had a huge wave which propagated towards the shore and took them away. So the relative size of a 10-meter wave is shown here. This is the initial warning. You see that the water line in the top picture, the water line has receded, exposing a greater portion of the seabed. And the next picture, the bottom one, you see how the waves are running towards the coast. So satellite imageries can play a very dominant role in the case of the tsunami warning systems or inundation maps, etc. So this shows in the case of Sri Lanka, how that is just prior to the tsunami, and you see the recedence of the water line, and then you see the propagation of the tsunami into the land. Shoreline in this case has receded up to about 343 meters in the case of Sri Lanka, and the water line has flooded up to a distance of nearly 1.5 kilometers into the land and destroying, leading to a big catastrophe there. Now going back here in the present case, the tsunami wave, some of the magnitudes are provided here. This is 4 kilometers. This is the depth at which the tsunami occurred. At what location? At which location it was? The velocity was something like 750 kilometers per hour, 713 kilometers per hour, and when it reaches the land at a depth of about 10 meters, you see that it is around of the order of 36 kilometers per hour. So this is how. So you have a long period wave, and then you have the magnifying and the steepening of the water level, and then you have the inundation. As I stated earlier, the velocity is just square root of g into water depth. In the case of time travel to India, so you have within 10 minutes, so then this is 50 minutes, 120 minutes, it's reached, within 2 hours it reaches Sri Lanka, and within about within another 10 minutes it reached Chennai, and within another 1 hour it reached this part. So this was the first animation that was available on the net, showing how the waves, how the tsunami waves traveled from the generation point. If you look at this thing, you will see that people who are working in the area of ocean waves, you will see that this island has diffracted the waves. You can see this, and the diffracted waves hit this part, and this part was one of the most damaging area, which is called as Nagapatnam, and it affected all these areas. So you can see some of these areas, but these were not that much affected, but the most affected are which will be illustrated in the next figure. And then the southern part of the Sri Lankan island also diffracted the waves, and we had effect on the tip of Indian peninsula as well as along the west coast of India. So this is the scenario how the entire place was disturbed, and in fact they have recorded some of the locations. They have recorded the water level. So it has reached Australia, as well as some of the disturbances was felt even in South Africa. So, but we are talking only mostly affected countries are somewhere here, as all of us know. As far as India is concerned, so this is the area which is very badly affected. So I would say that this area A was not affected because it was under the shadow area of Sri Lanka, and in fact Sri Lanka saved that portion of the land. And this is the area which is called as the Nagapattinam, where we had a lot of casualties and a lot of damages, and further here we also had a lot of damages. So and here this is another state which is called as Andhra Pradesh. Andhra Pradesh was not that affected when compared to Tamil Nadu. The most affected state was the state of Tamil Nadu. So if you look at some of the movies which you have already seen, so I'll just this will help you to recollect what was happened. So if you look, the top one is Malaysia, and the bottom one is the Indian tip of Indian peninsula. So you saw earlier, just before the movie started, you saw that a greater portion of the land in this case was exposed. There was a retreat of the shoreline, and now it has started propagating, and you see the waves propagating. And you see this statue, there was water spray up to the top of the statue, but the run-up, the wave run-up itself was up to the pedestal of this statue. And a few tourists were also trapped here, and then they were rescued later after the tsunami subsided. So you can just see how the tsunami is now approaching. So there, the top one was the trapping of a boy in tsunami, and now you can see the tsunami approaching the statue. This is from one of our local TV. Okay, this is what I wanted to show you. So it has reached almost the pedestal of this. We will have yet another picture of movie of this later. So this is Sri Lanka, and this is in the case of Thailand, how the tsunami penetrated. So now coming back to the Tamil Nadu state where I come from, the damages typically the damages are shown here in this transparency. At some locations you see the tsunami run-up was up to this height, and this is at a distance of about 1 kilometer from the coast. And this is a collapse of a bridge, and these are all some of the other damages. So soon after the tsunami, this is Marina Beach, that is in Chennai, in the city of Chennai. It's one of the longest beaches in the world, and it's a very good recreation place. And you see, immediately after the tsunami, it took several hours for the water to drain into the ocean, and because this was totally unexpected, and the entire life was disturbed. The destructive power of the tsunami. So you can see the house which was, so most of this destruction was when the tsunami entered, and when it was receding, it was taking a lot of debris, as well as when it was returning, it was having much velocity, creating a scour at the toe of the obstructions, and then leading to damage. And you see the shutter, the iron shutter itself has been damaged. So how do we manage this? See, location of tide gauges along the coast can give us some kind of useful information. As far as India is concerned, the network of our tide gauges are shown here. The maximum tide is somewhere here. It's of the order of, the tidal range is of the order of 8 meters, and the tidal range of this area is of the order of about 3 to 4 meters. But along the southwest, along the south coast, the order of range of tidal range is only of the order of 1 meter. So all our tide gauges, at least in Chennai port and some of the other ports, the tide gauges are designed for a maximum range of 3 meters. So when we looked at the tidal gauge recordings, you can see this is for the location where I have, this is the figure which I have shown. So you see that at 8:30 hours, and after that you see the signal, that is the tide gauge is really destroyed. So similarly for the other one, that is somewhere here. So that means that the tidal water level was much higher than 3 meters at the locations of some of these tide gauges. So this is somewhere near Goa, but there was not much of inundation of the tsunami. The other problem concerning the tsunami is harbors. Once a long period waves, my friends who are working in the coastal engineering, they should be knowing, once a long period wave enters into the harbor, then it is a big problem. That is, you have a lot of problems. For example, if this is a harbor, is just can be a natural harbor or artificial harbor. Artificial harbor is built with the help of breakwaters, as you can see by these two lines. This is one breakwater and this is one breakwater. When you design this breakwater, you try to fix the alignment in such a way that there is always calmness inside the harbor, so that the vessels can be berthed with safety. So when such a long wave enters the harbor, this is the scenario you can have. That is, there will be a considerable amount of oscillation, and which will be continuous. Considerable amount of oscillation, and it will be continuous. This will lead to the tearing of the mooring lines, which that is, the mooring lines are used to berth the vessels. So the mooring lines can snap, and the boats can go and collide with each other, and leading to a big problem. So this is basically, we look in the case of, so this is what has happened in most of the harbors. So this is one place which is called as Nagapatnam. That is the tip of the place where I said that the diffracted waves from Sri Lanka had a significant effect, and you see all the boats have been lifted up over the berthing structure, and some of the boats have traveled several meters into the land. It got lifted, and it was, and in fact many people had to search for their boats, and some of their boats were something like 1 kilometer away from the shoreline. So tsunami effects, you have the effects on coastal structures were selective, but human life was very severe, property very bad, and coastal landforms, the alterations of coastal landforms was selective, and surface and actually even the shallow water, freshwater bodies are also were affected. I mean, I am talking about the salinity intrusion into the land. Then generally, if you have a coastal flora, it was affected generally. Animal life was not affected, not much affected, because probably they have the sixth sense. And coastal fauna, that was affected occasionally. If you see the major impacts in the foreshore, modification of the beachfront, concentration of the heavies as places, breaches of beach ridges, and also the flattening of foreshore and adjacent areas. Now, this was the scenario, and the problem was very severe, and we need to take up, it was taken up on a war footing, and then I was made the consultant for the Tamil Nadu state, wherein I was requested to tour the entire state and come up with I am not a tsunami expert, I am only a coastal engineering person. So I just toured the entire state for about 2 weeks probably, and then prepared the report, and just before I left India to Germany, I have handed over the report, and this is something like a concept report, and the details will be worked out. People who are working in this area should be in a position to understand what I am talking about. So the entire stretch of the coast, this is the stretch of the coast, and this is up to this point is Chennai region, and up to this point is the Trichy region, and then I am talking about this region, etc. Because this region was not affected by the tsunami. So the tsunami direction is indicated here. So let us talk about this portion. I am talking only about this portion because I don't have a type of a logo where I can make you recollect what the location what I am talking about. Typical effects. You have the opening of the river mouths. This is a big problem in many of the countries, particularly in the developing nations, where you have the closing of river mouths. For India, we have a sediment transport which is to the extent of 1 million meter cube per year, which is one of the largest in the world. That is 1 million meter cubed of sand is moving towards the north continuously. Okay. When it is moving continuously, it goes and deposits near the river mouths. And when you look at India, most of the Indian rivers drain into the Bay of Bengal. That is, if you look at this, most of the rivers drain into the Bay of Bengal. And here you have the sediment transport moving along the coast in this direction. And when you have the river mouths, all the river mouths, you get filled up with the sand. And that becomes a big problem because the rivers become stagnant, leading to breeding grounds of mosquitoes, and it's health hazards. And I do not have to tell what are the side effects when you have the stagnant water. So one good thing about the tsunami is that it almost opened up all the river mouths. That was a welcome change. And some of the seawalls. Seawalls are constructed to protect the land from coastal erosion. So some of this toe erosion started, and several places we had erosion of the toe. So this is typically in a location called Mahabalipuram. I don't know some of you if you had been to India in my state. This is one of the most famous tourist spot. And you see at the same location from the balcony it has been observed. And during the tsunami and before the tsunami, you can see the beach here. Now here you see it's all filled up with the ocean waves. So this is a temple in the same place which I am talking about. Mahabalipuram, and this is from archaeological point of view is also very important, very important for us. So what happened in this case? So there were centuries back we had about 7 temples. These are all rock temples, and out of the 6 temples got submerged centuries back, and there was only 1 temple which had to be restored by the archaeological department. This happened sometime mid of 70s, and during the tsunami, what happened is, which no one has really seen, and some of these temples got exposed because of the retreat of the shoreline towards the ocean. And this, but around this temple, this is a flat ground. Whenever you have a flat beach, it is very dangerous, because when the tsunami comes, it will just like that move, and you have a lot of problems. So in this case, being a flat ground, you had the seawater entering into the unprotected coast, leading to significant damages. Now, I will just move slightly on the coastal engineering aspect. So this is to illustrate this coastal engineering aspect. I am taking this Chennai. We have the Chennai harbor. So this is the Chennai harbor, and when the sand is moving in this direction, this presence of this structure will lead to deposition of sand, and this is nothing but the formation of Marina Beach, which we have seen earlier, and we will have a significant coastal erosion on this side. So in order to control this coastal erosion, we have several types of structures, and here one commonly adopted structure is a seawall, which was tried for about 40 years and it was not successful. Then we had started constructing what is called as a groin field, which I will show you later. And this groin field, how it behaved during the tsunami propagation, can be seen with the help of this slides. So in this case, so I am just showing you the groins. 1, 2, 3, 4, 6 groins are there. You see that once the groins were placed, the groins are structures which are getting into the sea, and these are constructed by dumping boulders. I mean the rock, the huge rocks. And if you look at this, in an eroding area, after the construction of the groins, we had the beach build-up, and you can see the beach buildup. These are all the remote sensing imageries. Now, going into the actual field measurement, this was the kind of, I am just talking about these two groins. So here we had a beach buildup of about 3,700 square meters. So the work commenced in the last year in May, and the shoreline which is shown here is about say 4 months later, 3 months later. So we had so much of beach. And now moving on to 25th of August, you see around something like 7,000 square meter. We won the beach. And now this led to something like 8,800 square meter in September, 14th September. Now you see that whatever we have gained was lost due to the action of tsunami. So tsunami was something like 26th, and this is 6th of January. So 6th of January we have lost something like almost 50% of the beach to the ocean. So we were a bit upset, and then when we did the further survey, then we were quite happy that whatever sand was taken away by the tsunami was brought back. Not only brought back, it brought back additional sand, as you can see. This is one important phenomena which we have observed during the propagation of the tsunami, that is in between two groins. So we did this post-tsunami survey. The method was using the local villagers, trying to find out up to what height the water has run. So in this case, you see that the water has run about, something like 4-5 meters. So in this case, so these are some things which I need to talk about, wave run-up, etc. I will not tell here, and instead I'll just proceed. And land, and whenever we have narrow strips of land in between sea and the coast, and when we have parallel water bodies, and that is where we have the inundation. When I say inundation, propagation of water from the ocean into the land. For example, in this case, this is what is called as a Kadalur port. So this is Kadalur port, and here in this case, this area was very badly inundated. That is, water penetrated into about 1 to 1.5 kilometers. So how do we protect this coast? The concept is there are two rivers here. So construction of two training walls, again it's something like groins, and so again train this river mouth here, and then have a groin field as shown here, so that you will have beach buildup and the tsunami run-up can reduce. In addition to that, you also have, in addition to the groin field, we have proposed structure as shown here. So the curvature here which is shown, this curvature will reduce the run-up, because the idea is to reduce the run-up so that the inundation is reduced significantly. So in this particular area that is close to the Kadalur port, this river, you will see that this river is connected to the ocean. This land, the beach, was something like plus 6 meters above MSN. So this area was not at all affected. So people were happy, but unfortunately, the water entered into the river, and people this area is thickly populated. So most of the people had lost their lives because the water tried to penetrate into this water body, and instead of no one had any problem from the coast, but the water penetrated through the river. So these are so when you have waves moving on flat and steep beaches, this is what would happen. You look at the houses as well as the trees. So in the case of a flat beach, you have problems, but in the case of a steep beach, we do not have much of problems. So now, so this is the reality. So this is when the tsunami was penetrating. This is, we are talking about 500 meters from the ocean, and so the tsunami has traveled, and you see what happened, and it looks almost like a flood. So this is somewhere near what is called as Thirumullai Vasal in Tamil Nadu. This is for the benefit of students who have come from India. They themselves, they may ask me, where is Tirumallai Vasal? It's Tamil Nadu. So what I understand was that the whole house was submerged. The whole house was submerged when they had continuous, because people got scared and they ran away. And this was just before, I think they had two waves. So the first wave penetration was during this time. So you can see the flooding of water, and this flooding reached up to the road, which is main road, which is approximately around 1.5 kilometers from the shoreline. So now we move on to this area, which was also very badly affected. So you can see this is one area which is South India, and this shows how the tsunami has really penetrated. So you see the continuous pumping of the ocean water into the land, and what kind of protection measure we can think of against tsunami. So that's it about this movie. It goes on for. This again, that area of Kanyakumari, I just wanted to show you the splash. As you can see that it is much higher than the statue. So effects of river mouths and shoreline, I have already shown you damage of the seawall as well as new erosions, bridge breaking. So we move on to this location, that is somewhere here. This was again one of the worst affected. The pity is that this is the sea and this is the shoreline. All these buildings were just completely damaged because of the tsunami, because the height of the tsunami around this location was of the order of 8 to 10 meters. 8 to 10 meters. Many buildings got submerged. And there is a canal here, which is called as AVM Canal. And for these people to go into the main road, this is only the bridge, but there are several such bridges along the canal, but at a larger interval. So when the tsunami came in, these people, they, out of total frustration as well as confusion, many of the people could not identify where exactly is the bridge, and they got trapped in the canal. And at this location, something like 250 to 300 bodies were removed. So at the same location, the tsunami run at a distance of about 1 kilometer is shown here. That is the tsunami run up. That is water level. All these houses were submerged, and all these buildings were removed. And this is the bridge which I am showing. This is the bridge which I was telling. So you look at the flatness. The ground is quite flat up to the ocean, and so which has helped in the propagation of the ocean. So you look at the church at this location. As I told you earlier, the tsunami run-up was of the order of 10 meters. You see that the entire church has been ripped off except the front wall of the church. And you see this cover again. For this location, what is the kind of solution we can think of? So we thought of several locations, several solutions. So for example, in the case of nuclear power plants, particularly countries, particularly of Japan, what they do is they construct offshore breakwaters. Even in the country of Korea, they construct what is called as offshore breakwater. This is one important area which is thickly populated and needs to be protected. So what we saw is that we see a jetty here, existing jetty, which is not being used that much for berthing of the fishing vessels. So in order to take the advantage of the jetty, we have proposed 2 breakwaters here in order to protect this portion of the land. And on the land side, so this will help in the case of reducing the tsunami run-up. And the top level of this is fixed approximately at 5.5 meters. But when we do the coastal protection along the coast, so this is the kind of concept which we are talking about. And you have a wall here, which is with a top level of +7, so as to give some relief. And we are also planning, we have proposed some kind of earth fill and also plantations, because plantations very highly help in the reduction of the tsunami run-up. So this is yet another place which is called as Tiruchendur. Here again you see that the exposure of the seabed out, and which was never seen by the local people. This type of a scenario is first time in their life for all of them. So now we move on to the next area, which is called as the Trichy region. So the satellite imageries can play a very important role. So this is how it looks like. So this is 18th December and this is 28th December. So you see that the satellite imagery, from the satellite imageries you see this water, inundation of water. So this gives us an idea, but fortunately this area is not inhabited because it's only a marshy land. So this is the one which was just above the Sri Lankan coast, which was getting hit, which was having maximum damage. The type of damage here is, as we have seen, collision of boats as well as the bridges, etc. And here what the local people have started doing is construction of sand bunds. So this is another idea, but they lack knowledge. They hear from people and then start doing something else. So for example, people were talking about plantations. So plantations near the coast is extremely important, and it will help in the reduction of tsunami runoff. But not with such a huge spacing. Such a huge spacing is not going to help at all. So we have to train the local people in the case of plantations, but because there are several types of plants which will be very useful in. So here, tidal flats. The entire area was, this is Nagapattinam, the entire area completely got smashed because of this tsunami. At certain locations, what we are talking about is tsunami has entered, but not much of life lost, but to be on safe side, because people do not visit that place very frequently, but maybe sometimes, occasionally. So this is a famous church, which is called as Velangani Church, again South Tamil Nadu. So here the idea is to protect. How do we do this? So there is a river, so you dredge this river because there is a lot of sandbar formation. Dredge this river, then nourish this and use this sand for building a sand dune here. And then before that you have a plantation. And then as a secondary type of soldiers, you have buffer blocks. This is on a long-term solution. So when we talk about mitigation measures, we have to consider both short-term as well as long-term. This is long-term because it's not going to be affected immediately. Even in case tsunami comes, it may not be that dangerous. So soon after the tsunami, there were a number of pictures, movies showing different harbors. So these are all small harbors. It's not, except the bottom one, this is a major port, but all the other three are smaller minor ports. So these are self-explanatory, that is impact to roads. Now moving on to the west coast. West coast also was very significantly affected, as we have seen here. So these are the areas which was very badly affected. This area I have already concentrated when I spoke about the road and people getting trapped near the canal. And when we look at the overall tsunami impact assessment, this is the scenario what we get. And you see that these are all some of the locations. The thickness indicates the magnitude of the tsunami run-up. So now we move on to Andaman Islands, because that also belongs to India. So you see, this is how the apparent movement of islands look like on a long-term basis. And when we looked at the satellite images, it gives some kind of an idea. For example, here if you look at this one of the islands, see you see that the inundation has gone up, and see the island is almost detached. And here again there is heavy inundation, where you see that a significant portion of this smaller island is affected very badly. So damage to structures. So this is port and harbor structures also, including the conventional buildings. And tsunami coming back, this satellite imagery shows the effect of tsunami on the river mouth. This is in Madras city. That is, you see the closure, and this you see the opening, and similarly you see the opening of the river mouths along our different river mouths. So the other concept is bioshields. Bioshields means having we call it bioshields because we are going for these plantations. See, so you look at the plants. There are several reasons, because it's not just like that. It's coming that you plant some trees. Because plants have a very important role to play, particularly its roots. So they can offer some kind of a resistance to erosion. And it has been scientifically proved that these roots are very effective in preventing soil erosion. So moving on to estuaries, that is where you have connection of fresh water and the seawater. In estuaries, the mangroves grow very well. And for the Indian coast, there were a number of stretches of the coast where mangroves really helped in the reduction of the tsunami run-up. So in fact, their roots are classified, have different shapes as shown here, and these roots are also having some kind of reducing power, reduction of the tsunami run-up. So this is what I wanted to tell you, and I would like to place on record the acknowledgements. That is NGRI, NOAA, NRSA Survey of India, the Hindu, several websites, USGS, my colleagues, my friends, my students, as well as my well-wishers. Tsunami statistics. Worldwide, 94 in the past 100 years has caused something like 51,000 deaths. The tsunami of 2004 has cost about 250,000 or even more. So this is the basic. So this gives us the magnitude of the challenge before us. So it was just a few seconds where all it took, and sadly it took all. Never see you tsunami again, in my life at least. So any comments and suggestions, you can contact me. And I once again thank you for giving me an opportunity and for your patient listening. And I think exactly I have taken 2 minutes extra. Okay. Thank you.